Okay, let's take a look at these mathematical statements and turn them into logical propositions. And let's find the negation of both. First off, x is less than 4 or x equals 4. Clearly, the statement is x is less than 4 or x is equal to 4. And that is the statement written in terms of a logical proposition. To get the negation, and I'll write this in red, the negation of this that's the same as saying that the x is not less than 4, and it is false that x is equal to 4. And the last one can be written more succinctly as x is not less than 4 and x is not equal to 4. So that would be the negation of the first one. Now this makes common sense. Obviously this is the same thing as saying that x is less than or equal to 4. So on the number line, this would be, here's 4, and I would plot that on the number line like this. Now, you've probably been doing this as Algebra 1, plotting that on the number line. Now, for the other one, the negation of this, if x is not less than 4 and x is not equal to 4, then the only option that's left is that x is greater than 4. And that would be this part of the number line over here. So clearly, this part of the number line is the opposite, the complement of this part of the number line, and so this kind of makes sense. Okay, second problem. X is less than or equal to 5, and x is greater than or equal to negative 5. So written as a mathematical as a logical proposition, x is less than or equal to 5, and x is greater than or equal to negative 5. The negation of this statement, x is less than or equal to 5, and x is greater than or equal to negative 5. That would be that the first statement is false, or the second statement is false. And that would be the same thing as saying that x is greater than 5, or that x is less than negative 5. Now again, this makes sense. The first part here on the number line, if I were to plot negative 5 and plus 5, that would be all the points that are in between negative 5 and plus 5, including the endpoints. So the first set of inequalities would be this. The negation would be, well, it could be everything that's to the right of 5, or everything that's to the left of negative 5. And once again, the part that I'm shading is exactly opposite of the part that was shaded on the top picture. So that would be the first couple of examples, and I put these examples up just to remind ourselves of these simple properties from Algebra 1 class and how the De Morgan's laws can be connected to the simple ideas from Algebra 1. Alright, the next example is more complicated. For every real number x, there is exactly real number y, one real number y, such that the point xy is on the graph. Okay, so to do this problem, we'll first define the predicate function, g of xy, to mean that the point xy is on the graph. Then we have for every value of x, there exists a number y such that the point xy is on the graph. Now this doesn't quite do it because the way this is stated right now is that there is at least one point y, but I want to state that there is exactly one point y. So I want to have that this is true, that there is at least one point y, and it's also true that for every point z, if z is not equal to y, then that means that the point gz is not on the graph. So not only is the point xy on the graph, but x anything else is not on the graph. So that would be the fullness of this, that there's at least one point on the graph, and also there is exactly one point on the graph. Anything else besides y is not on the graph. We could have flipped this around and used the contrapositive, so what I'm about to write is also a correct way of writing this. For every x, there exists a y such that xy is on the graph, and for all other points z, if xz is on the graph, that implies that z is equal to y. So if xz is on the graph, then z is equal to y, and furthermore, the point xy is on the graph. So those are the original statements. To get the negation of this, so I'm going to negate now this statement. So I'm going to recopy in red what I just wrote, and I'll use the contrapositive that I just wrote. And also, let me change the contrapositive to the not P or Q form. So that's, if P implies Q is the same as not P or Q. Then taking the negation, we get there exists an x such that for every value of y, not g of x, y, or there exists a z such that the negation of this holds. So let me do that in two steps. The negation of gxz, or z equals y. And then I'll apply De Morgan's laws to simplify that. There exists an x such that for every y, not g of xy, or there exists a z such that g of xz, and it is false that z is equal to y. And one more line. There exists an x such that for every y, not g of xy, or there exists a z such that g of xz and z does not equal y. Okay, now why does this make sense? For every x, there exists an x such that for every value of y, either the point xy is not on the graph. So this would be the case that xy is not on the graph at all, or it could be that xy is on the graph, but there's some other second point such that z is not equal to y, but xz is on the graph. So that would be, either way, that would contradict the idea of being there exactly one real number. This would be the case of none, and this would be the case of two or more. So that would be the next one. Okay, continuing. The next one, there is a vertical line that intersects the graph at least twice. This is a familiar concept from algebra. So let's define a couple of predicate functions. Let's define the intersect function, I of L, to mean that line L intersects the graph at least twice. And let V of L be that line L is vertical. Then there exists a line such that the line is vertical and the line intersects the graph at least twice. So that would be the original statement. Now to take the negation of this statement, and I'll do this in red, the negation of what I just wrote. Okay, so that'll mean that for every line, I have the negation of this. And then by De Morgan's laws, that means for every line, the line is not vertical, or the line does not intersect the graph at least twice. And if I consider this as not P or Q, then I could rewrite this as for every line, not that P implies Q, where my Q is not I of L. So the opposite would be that for every line, if the line is vertical, then it does not intersect the graph at least twice. So that would be the negation of the original statement. And of course, what I've written here is basically the vertical line test from algebra. Okay. Next, let's take a look at one of two different limit ideas. So you may not recognize this, but this is the idea of a limit from calculus. For every positive number epsilon, there is a positive number delta, such that f of x minus L is less than epsilon whenever 0 minus x minus c is less than delta. So for this one, there's actually 3 quantifiers. 2 of them are explicit. For every epsilon greater than 0, there exists another number, delta greater than 0, which may depend on epsilon, such that for every x that satisfies this inequality here, so for every x that satisfies this inequality, if it satisfies that inequality, then f of x minus L is less than epsilon. And so that would be the original statement. And this is from calculus, the definition of the limit as x goes to c of f of x equals L, where c is what x approaches and L is what the function approaches. Okay, let's now take the negation of this. So the negation of this statement, so I'm going to rewrite this. And when I rewrite this, let me change this implication into not P or Q form. So not the first thing or the second thing. Okay, so taking the negation, this means that there exists an epsilon greater than 0, such that for every delta greater than 0, there exists an x, such that the negation of what's in parentheses here holds. So the negation of 0 minus x minus c less than delta. I should have closed those parentheses. Or f of x minus L is less than epsilon. That closes the negation, and that closes this one. Well, this closes the or, and this closes the negation. Okay, so that means that there exists an epsilon greater than 0, such that for every delta greater than 0, there is a number x, such that the negation of this first statement would be the original statement, by the double negation rule. Then by De Morgan's laws, this or flips to an and. Then I have the negation of the last statement. And I can get rid of this not, because the opposite of something being less than epsilon is that the something is greater than or equal to epsilon. So there exists a delta greater than 0, such that for every delta greater than 0, there is a number x, such that x is in the range that's specified, and f of x minus L is greater than or equal to epsilon in absolute value. So that would be the negation of the original statement for where the limit does exist. Finally, let's take a look at this last way of expressing a limit. This time, this phrase is interpreted that the limit of n goes to infinity of a sub n is equal to L. Okay, so let's read this again. For every epsilon greater than 0, there exists a number n such that for every n, if n is greater than or equal to n, capital N, that implies that a sub n minus L is less than epsilon. So as long as n is greater than capital N, then this inequality holds. To find the negation, I'll switch to red. For every epsilon greater than 0, there exists an n such that for every little n, now I'll write this in not P or Q form, not the first or the second. Okay, so then applying the negation, the for every becomes a there exists an epsilon greater than 0. The there exists becomes a for every n. There exists an n such that the negation of this holds. So the negation of n greater or equal to n, or a sub n minus L is less than epsilon, which becomes there exists an epsilon greater than 0, such that for every capital N there is an n, such that n is greater than or equal to n, the negation of the first statement, and I should add parentheses there, and the negation of the second statement. And so finally, that's there exists an epsilon greater than 0, such that for every integer n, there exists an n which is bigger than capital N, and a sub n minus L is greater than or equal to epsilon. So that would be the negation of this last statement.